Nonlinear control. My name's Chris. You can just call me Chris. It's fine. So I just asked you all to review all the materials that I put up on D2L. Hopefully you got a chance to read through those. So I was just going to open it up for questions to begin the lecture, assuming that you've read all the information. So Josh has a question for me.
Yeah. So I got the Indian edition of the textbook, so I'm wondering if that's okay for the test questions or not.
I think it'll be just fine for the test questions. Okay. And like I told him, you won't know exactly, I won't give you a page number or anything for each question, but it's pretty obvious where each question is based on from the appendices. So you basically have to study the appendices, but it is an open book quiz, so you will have the textbook there available for you to reference when you're doing your questions. So it's not, so it won't be asking you to copy stuff out of the textbook, obviously. The quiz will be actually asking you to apply this stuff, to work out formulas or work out norms of vectors or deal with matrices or things like that. So you'll actually have to do the mathematical operations, but you have the book to refer to how to actually do it. So that quiz will be in the third week of lectures, September 25th. Any other questions about the course? There must be some.
Oh, we might want to clarify that I'm not the TA, even if it says that on D2L.
The D2L says you're the TA? Oh, because I registered you as a TA, yeah. So you can see the course. So Rachel's not the official TA, but feel free to ask her any questions. She'd be so happy to answer any of them. Question?
I did have one question. How is this course going to differ from the intelligent controls course?
I don't know. It's a little bit different. It's more mathematical, and I get into more of the theory. In intelligent control, I just kind of tried to cover the basics so we could get to the idea of neural networks and fuzzy logic as quickly as possible and cover as much of that material. And I tried to cram a little bit of nonlinear theory into the beginning, just so you could do it. So this is more comprehensive, where we go through a lot more of the nonlinear theory and you learn about nonlinear systems. This course, in that course, the intelligent control course, I tended to do 2-hour lectures. In this course, at least for the first few lectures, it will be full 3-hour lectures, although I'll give you a little break in the middle. But in the first few weeks, there's definitely a lot more material in this course. And I'm giving you a quiz, so I actually want you to know all the mathematical background in this course, whereas in the intelligent control, you really just had to know enough so you could do your project. But I'm more kind of focused on giving you a broad understanding of nonlinear systems in this course. Any questions? Questions about the projects? It's 90% of your mark is a project, so. Any questions about it? Yeah?
Will we be given sort of an example of the plant for a robot arm? Because that was one of the options.
Yeah, if you want to do the flexible joint robot, in a way that's going to be easiest, because I'll kind of gear the lectures towards that, and I'll provide you code to get you started. So what I'm really keen on, I never did this before in this course, but now I like using MATLAB C coder. So you can program in MATLAB, but compile it in C, and it runs 30 times faster than regular MATLAB code.
Oh, cool.
So before, I didn't really want to encourage students too much to do massive simulations, just because their MATLAB code would be so slow to run, and I didn't really want people programming in C because it's too time consuming. So now we kind of have the best of both worlds. So now we can do big projects, but compile it in C, and have it run fast enough that it's kind of reasonable to do as a course project.
Oh, that's cool.
So if you're doing the flexible joint robot project, I'll definitely be giving you code to help you out, get you started, although I do want you to program some of it yourself. So I won't just give you a working example.
Okay.
And Rachel's not allowed to give out her working example. Sally's not allowed to give out his working example. So keep it confidential. So I'll provide enough that makes it easy for you, but doesn't do all the work for you. So probably what I'll do, what I'm thinking of doing is actually giving you the code for a rigid robot, and then you can convert it into a flexible joint robot yourself, which is fairly straightforward once you have the rigid robot code. Then you
Okay.
can see how it all interacts and works. And doing it to flexible joint robot is just pretty easy. So how many people are working on an MSc thesis or a PhD thesis where they have to control a system, so they're going to not do the flexible joint robot, they're going to do the system that's their thesis is about? How many people are going to basically pick project 2? Anyone? So what system are you going to look at? You're not doing a thesis yet.
Not yet. I'm not even in the program yet.
Yeah. So you might be better off doing project 1.
Okay.
But you have to come and talk to me. There's no hard and fast rules with a project. Everything's negotiable, but you do have to talk to me about the project, especially if you're going to do anything different. So if you're doing kind of the same project, technically everyone should come and actually discuss the project with me just for a few seconds at least to tell me what they're up to. But if it's basically the same thing everybody else is doing, it's not going to be a problem. But if you want to do something unique, then maybe we want to sit down and discuss it so we can talk about the scope of the project and how you'd be evaluated on it and stuff. Any other questions? So I'm just going to kind of introduce ways we kind of think about nonlinear systems and analyze nonlinear systems in kind of simple ways, just to start off with. So suppose we have a second order nonlinear system. Say y double dot equals f and y dot plus g of u of t. Where g is a constant and u is the control input. That's a pretty typical kind of system we're interested in that we can deal with. Obviously, when you talk about nonlinear systems, they can be more general than that, but this is typically the kind of system we're able to control and that often appears in real life applications. So this kind of system we're especially interested in, put it that way. So in state space, you have x1 equals y, x2 equals y dot, and we have x1 dot equals x2, x2 dot equals f of x and 1 and 2 plus g of u of t, g times u of t. So we could use MATLAB to simulate in Simulink. And if you did use Simulink, it would really look something like this. There's different ways of doing it, but so that's probably the way I do it is Simulink. How many people have used MATLAB's Simulink before? So a few people haven't. So in MATLAB you can type in Simulink and the Simulink window will pop up and you can basically do graphical programming essentially. The big advantage of Simulink over writing code is basically the integrators. So when you write code, it's a bit tricky to integrate things. So Simulink especially makes integrating really easy because you pull out these 1/s blocks and it integrates for you. Also, there are advantages to thinking graphically when you can see like a nice block diagram of the system rather than coding, straight coding. It's a little, when you're coding you have to like remember to sit down and do a block diagram off on the side. And some people kind of forget to do that, but this actually forces you to create a block diagram as you go. So it's kind of nice for just engineering thinking. So I guess traditionally in this course and in Intelligent Control 2, most people probably would have done their projects in Simulink. Like I said, this year we're probably going to get away from that. So we can do like a two-link flexible joint robot. We'll probably do it, as far as I know, it's not possible to take a Simulink code like this and convert it to C code. So that's like, maybe next year they'll have invented that. But for now, I'm going to have to like probably leave Simulink behind for the projects and go into straight MATLAB code all the time. But I do encourage you to always draw block diagrams yourself of the system you're dealing with, especially when you're coding. But I will give Simulink examples during class. So they'll be up on D2L, I think they're up on D2L already actually, and you can download them and play with them yourself. So you can learn Simulink in this course as well if you're interested. So this is how I would approach the system. It's not the only solution. There's different ways of creating this in Simulink, but this is a nice way because you can see these states individually. You can see kind of the individual dynamics of what's going on here. And then you're kind of looking at the outputs. So these are the two outputs. So typically when you'd run a Simulink diagram, simulation, you would kind of graph the outputs. So we could plot x1 and x2 versus time. So maybe this is like a step input. So maybe x1 looks like this. Maybe x2 looks like this. Because we're really talking about, if this is a mechanical system, we're talking about position and velocity for x1 and x2 here. But we learned a bit more maybe, sometimes, if we eliminate time and plot the trajectories on the state plane, which is also called the phase plane. So the state plane and phase plane are interchangeable terms. By the way, just give a yell if I start erasing something that you haven't copied down yet. Sometimes I do tend to lecture rather quickly. Need to be halted before I start erasing stuff. Don't feel shy about stopping me. So in the example we just did, it would look something like this. We looked at the, if you combine these two graphs together, basically you're eliminating time and plotting x2 as a function of x1, seemingly. So a family of trajectories starting from different initial conditions is called a phase portrait. So, my classic system to learn about nonlinear systems and nonlinear control is the good old pendulum. So we'll have a massless pendulum. Pendulum arm, I should say. Length L. Point mass at end of the arm. M. We'll have some linear friction here. B theta dot. So this is a nonlinear system. One thing that in real life that would make this system nonlinear would be the friction. But actually, for this simple model, I'm actually just going to use linear frictions. If I just have a constant times the velocity, that's just a linear term. But I could put a fancy friction like Coulomb friction or something in there. Static friction. I could put like a nonlinear friction term here to make it more realistic. So in real life, there are definitely nonlinearities from the friction itself. But where's the big nonlinearity in here, pendulum? What's a nonlinear term in pendulum dynamics?
The sign.
Yeah, so
Sign of change.
yeah, gravity, the torque from gravity is going to, there's going to be a sine theta term in there. So, it's different, like a normal, like a linear, and it kind of acts like a spring because it's bringing the pendulum back down to the bottom, right? So in a regular mechanical system where you did have a spring, usually you assume a linear spring model, where you have a spring constant times the deflection, so that makes it a linear system, although in reality, springs also are actually nonlinear, especially when you get far away from the equilibrium point of the spring. So, you know, when you have linear models, they are truly models. Like when you have a linear model of a real system, the real system always has nonlinearities in it that you're just ignoring for your linear model. Whereas when you do a nonlinear model of things, you can throw in as many nonlinearities as you like to try and kind of accurately model the nonlinear system and all the actual things that really do happen in a real physical system. So we won't get too realistic with this model. We'll just throw in a nonlinear term for the gravity. So if you want to see how this is derived, you can just look at the textbook. Basically, I'm just using, well, Newton's law is force equals mass times acceleration. When you have a rotational system, the equivalent is torque equals inertia times angular acceleration. So if you do torque equals inertia times angular acceleration, you can derive this beautiful equation here, where K1 is equal to gravitational acceleration constant G over L, and K2 is equal to my friction B over ml squared. So in reality, there's probably all kinds of nonlinear effects. I'm just capturing the largest nonlinear effect in this kind of simple model with that sine theta term. So if I'm using my state space, x1 equals theta, x2 equals theta dot, get a state space model, x1 dot equals x2, x2 dot equals negative k1 sine x1 minus k2 x2. Then I can do some phase portraits. So all I'm going to do is set up a little Simulink model for the system and run it in MATLAB. And like I said, for the phase portrait, one, I'm going to do it for a bunch of different initial conditions. And two, I'm going to not have time in my graphs. I'm going to have x2 on the vertical axis and x1 on the horizontal axis. So let's take a look at what that looks like. I guess I will. I'll graph it in time first. So this is my This is my Simulink model. Maybe I should turn the lights on. So you can see that indeed I did it differently than I drew on the board. So like I said, there's different ways of setting up your Simulink model. There's no unique solution. So, but this is equivalent to what I drew on the board. It gives you the same answer. So in this case, I'm just setting it up for different initial conditions. So I don't actually have an input here. So I didn't have. I was thinking like there's an electric motor here or something, like creating a torque at the joint. Then I would think of that as a control for the pendulum. Or if I had like something fancy like little jets, air jets or something, pushing air out at the point mass, that would also be a control torque. In that case, I would have like a control input on this side. But all I'm doing is running it for different initial conditions. So the different initial conditions get set up inside the integrator. So I just set up the initial conditions for these integrators to be variables. And the variables I can set up in the MATLAB code. So the code looks like this, and so K is my G over L, and then rather than setting up K2, I set up the friction coefficient to be 0.5, and then these are my initial conditions, so I set them up as variables inside the Simulink model. I'm just calling this nonlinear pendulum model for MATLAB, and when I do it for one particular initial condition, this is what it looks like, so pretty straightforward. Both position and velocity have this kind of decaying exponential envelope, which is kind of what we expect from a linear system. So it just looks like, by eye you can't really tell that this one's particularly nonlinear. It doesn't look too strange, although sometimes nonlinear systems look very strange and it's obvious they're nonlinear even from looking at plots like this. But it's not obvious from looking at this that it's nonlinear actually. So let's look at that same trajectory in phase space. So it's kind of this kind of spiral effect coming into the origin. So the idea of a phase portrait is to do a bunch of different initial conditions. So each one of those dots is an initial condition. And if I'm just looking at this part here, it's not so obvious that it's nonlinear. But as soon as I see things like this going on over here, then it's, especially these ones here, then it's really obvious it's a nonlinear system, because a linear system would never do that. A linear system would look, basically nice and regular and going to the same point all the time. Yeah.
Would a linear system always spiral towards a certain point?
Well, yeah, because a linear system can only have one equilibrium point.
Oh, okay.
Whereas a nonlinear system can have multiple equilibrium points. Anyway, this gives us a nice general idea of how the system behaves for all these different initial conditions. So are there any questions about phase portraits or using Simulink or the pendulum or anything?
So is it a property of a nonlinear system that it will have more than two equilibrium points?
A nonlinear system has almost no rules, so it can have multiple equilibrium points or it could have one. But a linear system is yes, there's only one. Linear systems have all kinds of rules about them. Nonlinear systems could do almost anything. It's you really can't have much in the way of general statements about a nonlinear system.
So if we had a nonlinear system and it had one equilibrium point, that doesn't necessarily mean that it's a linear system.
That's right. Well, technically, I suppose I should have started off the lecture by giving the definitions of definition of linear systems, but that's kind of boring. But linear systems, probably you remember vaguely, they have the properties of superposition and homogeneity. But you can't, there's no kind of equivalent definition for a nonlinear system. Basically, anything that's not linear is nonlinear.
Does that mean if you have a like a poorly designed controller on a linear system that becomes unstable, does that make the resulting system nonlinear then if it's moving away from an equilibrium point?
You can have unstable linear systems.
Oh, okay.
That's because an equilibrium point can be an unstable equilibrium point.
Oh, okay.
Equilibrium points can be stable or unstable. Like in the pendulum, like, you know, this is a stable equilibrium point. This is an unstable equilibrium point, right?
Yeah. Okay.
Let's do the method of. Oh, I should make a note. You can also see the MATLAB code for the pendulum. In my book, it's on page 57 of the textbook. I don't know about Indian versions of the textbook. But anyway, there's some pendulum code there as well that's different than mine, so that might be interesting. You're kind of learning about MATLAB. It's the method of isoclines.
Yeah. In Indian version too.
Okay, good. A curve along which the trajectory slope is constant. If x dot equals f of x is a nonlinear system, the slope of the trajectory on the plane is, on the phase plane I should say,